Welcome everybody, welcome to Visma TechZone. My name is Ruud de Jong. I'm a solution architect for Visma Connect, and I'm gonna tell you a story on how we built a humongous messaging system which is used by an entire nation. But please, let's go to Visma Connect first. So Visma Connect is a company that I work for. We are located in The Hague in the Netherlands, and we joined the Visma group in 2019. But we have originally started in 2006, and we have dedicated ourselves to empower the digital society. We have successfully been involved in some of the most important mission critical and sensitive information and data sharing programs. Our services have become crucial enablers for a society in which institutions spend less time on administration, filing, and data collection. A society in which organizations can focus on their core business, whether it is policy making, healthcare, driving the flow of goods, or handling your financials. In the digital age, data is the most important raw material. This also means that we share more and more data with each other for all kinds of purposes. But how do you do that in a safe, fast, and controllable way? Well, Visma Connect takes the lead. Just as energy companies built the infrastructure that made the industrial revolution possible, Visma Connect is the utilities of the digital society. Our core services consist of standard business reporting, integration, and qualified messaging. So let's now go to the story. In the middle of the night, a long time ago, in an office building far away, the ops guys were in a maintenance windows. Production systems were shut down. MongoDB was about to get an upgrade from 3.4 to 4.0. This event was planned for weeks and weeks. It had been tested on different environments, each time with different issues. The craftsmanship of hand-built environments did not help. But now, this is production. We have more than 30 terabytes of data, which should not be affected by the upgrade. In this maintenance window, there's no time to restore any backups in case of failure, because, well, the dataset is simply too big. So this had to be a one-time right upgrade. Now, they were about to hit the upgrade button. But wait, maybe I need to go back even further. So, once upon a time, about 5 years ago, way before the age of containers and cloud, Visma Connect won a tender to build the nation's first humongous messaging system for Dutch federal government. A bit like email, but then closed, proprietary, and of course, more expensive. It had been built on a classical application server stack, yet having the ability to store messages for all the citizens of the Netherlands, coming from all sorts of Dutch government organizations. It had to be stored for unlimited amount of time. The peak performance will have to be something like 2.5 million messages per day, and the message can be up to 1 megabyte in size, so that means maybe 2.5 terabytes of data for the largest and busiest days of the year. The Dutch population is around 18 million people, and we have about 14 million people with message boxes, because only the adults are allowed to receive messages from the government. Anyway, this system was not a new system, it had a predecessor, and the predecessor was running at the Dutch DMV. So it was originally intended to remind drivers of cars for their upcoming annual car inspections and to send them all kinds of messages related to their cars. In the Netherlands, there are about 7.5 million cars on the road which need an annual checkup. That system could process about 500,000 messages per day at maximum. And this system actually worked great for many years. But then the Dutch tax office saw the system and they were very enthusiastic. They wanted to use it for their annual income tax messages So they wanted to replace the classical tax envelope, which is blue in the Netherlands, by the way, by a fancy digital PDF message to remind citizens to pay their taxes. Well, that meant that the load on the old system increased about tenfold and quickly exceeded the original design limits. So there had to be built a new system. So what did we have for system requirements? Well, the government would not be the government because they stated they wanted to have unlimited expandable storage for storing messages for unlimited time. So this is like, normally that would be relatively impossible. The peak performance was set about 45 messages per second and about 2.5 million messages per day. The original dataset at the time was about 12 terabytes in size for the old system, and that would probably grow up to 15 or 16 by the time we would migrate to the new system. And the original classic stacks involved products from the company with the blue logo. Soon it became clear that they, as in the company with the blue logo, could not provide the requested storage system at any reasonable price. From software developers, NoSQL solutions were proposed to handle this problem, but they didn't have a blue logo and were therefore rejected. That is how MongoDB came to the rescue. It needed years and years of talking between our company and our client up until the higher level in command, but finally MongoDB, which is a distributed NoSQL database, was about the only possible and affordable solution. So, because the company with the blue logo was still the preferred supplier for storage, we were only allowed to store the binaries of the PDFs into MongoDB, and all the rest had to be stored in the classical SQL databases. So, because we didn't have any experience, we flew in a couple of experts from MongoDB, and we had to make sure that we would build a system which can handle this kind of load and this kind of scale. I personally proposed a data model for MongoDB. It was only slightly adjusted by the MongoDB experts, so I was pretty confident in having a proper data model there. The programming of the application was way simpler than a classical database. You can actually run MongoDB locally, like in a Docker for example, and do full integration tests against a real database. Before you can actually commit your code, you can have full integration tests. So we were as a developers, we were very fond with the new MongoDB setup. So how does it look like? How do you set up a MongoDB for this solution? Well, there are different forms for deploying a MongoDB distribution solution for any kind of solution. But let's take a look at some of the examples. The first option would be a standalone instance. MongoDB says by itself in their own documentation, please do not use this for production since they lack replication and high availability. Only use this for development and testing. So in our solution, this would definitely not be an acceptable use case. The second option would be to use a replica set. A replica set usually contains 3 data nodes, 1 primary and 2 secondary. The secondaries will contain a copy of the primary, of course, but reads and writes will be usually done against the primary node, and it uses a system called oplog or change stream, which then sends the changes from the write actions from the primary to the secondaries. And whenever the primary node fails, a re-election decides which of the secondaries will be elected for primary. In our solution, the entire dataset, so 12 to 15 terabytes at start, simply would not fit on one single data node. Please keep in mind that hard disks nowadays might be large enough for this dataset, but at that time they were definitely a lot smaller. So what else is there available? And this is where we got our solution. It's called a sharded cluster. A sharded cluster is a collection of shards. It's called a sharded cluster. And each shard actually contains a subset of your sharded data. So a shard is then deployed as a replica set. So the replica set ensures that if the primary fails, the secondary can take over. And then you got a couple of those replica sets to form a collection. and that's called a sharded cluster. In order to manage the sharded cluster, you need a set of config servers, and the config servers contain metadata and configuration for the cluster, and it'll know where in which replica set will contain what kind of data. In order to access the sharded cluster, you need a set of routers, and routers work as an abstraction to the application and can forward requests directly to the correct shard. So this means that your application is not aware of accessing a very complicated setup like a sharded cluster. It'll simply contact one of the routers, which is the main access point for your application, and then the router will look in your request that you're doing for your data and will then forward this request to one of the shards where your data is. So how does then our production environment is going to look like? Well, the production environment that we had for this solution is a 2 data center solution. So that means that the application is deployed in 2 cells, each cell in 1 data center. All the primary SQL databases are in data center number 1, and all the secondary SQL databases are in data center number 2. So on failure of the primary database, manual interaction is needed to promote the secondary to primary status, and he can then take over the work. This is what you would expect from a classical SQL database. But now, how about MongoDB? Well, in MongoDB, things are a bit different. So first, let's take a look at the configuration. We didn't buy the hardware to run this solution, so we have to rent it or lease it from whatever provider that the government made available to us. And it soon became clear that if we wanted to have huge numbers of storage, that 4 terabyte per server was most cost effective. So this means that the primary and secondaries were all 4 terabytes, and that would create a shard size of 4 terabytes. So the initial data set from the old system was about 12 to 15 terabytes, and we wanted to start with at least twice that size, so somewhere in the 30 to 40 terabyte range. So that's why we decided on making the initial MongoDB cluster about 10 shards in size, which is about 40 terabytes of net storage. That would then contain 10 primary machines, 20 secondary machines, and 120 terabytes of raw disk capacity, which then would effectively be 40 terabytes for usage. But then how would we go for the relatively unlimited expandable storage? Well, our solution will never be unlimited, and the contract that we won was only for, 10 years or so. So this means that we would only have to be expandable for a reasonable amount of time. So given the requirements and the amount of data that should be added to the system, we thought about having to have a maximum of 100 shards. So we start off with 10 shards, and we could eventually increase more and more shards, and then eventually end up with 100 shards. The 100 shard version would be 400 terabytes of storage capacity with 100 primary machines and 200 secondary machines. We're talking here about 1.2 petabytes of raw disk capacity. This would definitely make this system one of the largest MongoDB clusters ever. So that's why it's called a humongous system. By the way, if you look in the documentation for Mongo, the name Mongo is actually a short piece for humongous. So they actually took the Mongo word from the humongous to name the system. Well, according to the growth rate of what our client suggested, we should have hit this mark, so 100 shards, about 7 or 8 years after going to production. But, of course, things in real life are always a bit different from the theory, because, that's how life goes, right? So there were a few issues. For example, our client didn't fancy public cloud and uses his own government certified data center with only one provider for hardware, networking and storage. So since we had to have lots and lots of storage, we needed the cheapest one available, which is still way, way overpriced. I mean, we wanted to have cheap disks, but that also meant an incredible slow disks. And how slow? Well, we're talking here about 50 IOPS per disk, while MongoDB recommends at least 2000 IOPS per disk. So this would definitely be an issue during peak performance. I mean, if we're doing peak performance like 45 messages per second, then the message can contain a couple of attachments, and each attachment would then require 3 write operations. So we're talking about like 500 write operations at least, and we only had 50. So yeah, that wouldn't really cut it. And to make matters worse, we also had to consider stuff like auto-balancing, which will happen during peak loads. So let me explain a bit on that as well. So what is auto-balancing? A MongoDB sharded cluster is a collection of documents, and these documents have a shard key. And the shard key is used to spread the documents across the shard. So the shard key is really an identifier for a shard. So it's not done on a document basis, but it's done on a chunk basis. So a document in MongoDB can have a maximum size of 16 megabytes, and a chunk can have a maximum size of 64 megabytes. So a chunk contains all documents with adjacent shard key values. So going from big to small, we first have a cluster. A cluster contains several shards. Each shard will contain several chunks, and each chunk will contain several documents. This is really important to explain to you how the auto-balancing works, because MongoDB balances chunks across shards, not documents. So let me show you how that works. So the MongoDB balancer is a background process which constantly moves chunks around shards in order to get an even distribution across all the nodes. So in our solution, when we have a massive insert on peak moments, all the created documents will have an object ID, because that's the default for Mongo, and that object ID will contain a timestamp, but the timestamps are then closely related because they happen at nearly the same time. So this means that on peak performance, all the new documents will be inserted in the same shard. This also means this shard will quickly fill up, and then the balancer will start moving chunks to other shards. So during peak insert on one shard, we get additional I/O from the balancer on the background, which further reduces the available IOPS in order to write our documents to the shard. So we did a few small tests, and it soon became clear that we needed to have some architectural solution for this problem. And that's how we go to the do not try this at home. So what we did is we switched off the auto balancing functionality. So that's something that you should generally not do. And we also created a shard key with a random number from 0 to 100. So remember, we start off with 10 shards in the beginning, but we want to have the ability to grow to 100 shards. So this means we mapped 10 shards keys per shard in to begin with. And then when we extend, we could actually spread out the shard keys across the new shards. So now during peak performance, all the new documents will have a shard key starting with a random number. So if you have a random number, this will evenly distribute all the new writes, even if they are more or less at the same moment, to all the different shards. So that means we're actually writing simultaneously across all data nodes, even if they have object IDs with timestamps which are very closely related. So effectively, this increased the IOPS from our system about tenfold, from 50 to 500 IOPS per second. So now we were only like 4 times slower than what MongoDB recommends. This at least solved our problems during peak load. But if you turn off auto balancing, coming back to the auto balancing feature, it can never be turned on. It's a non-reversible decision. So the data distribution across the shards with our custom shard key will have to be nearly perfect. MongoDB calls this kind of sharding hashed sharding. It'll scatter your data across your cluster and might not be ideal. For example, if you're doing a range-based query, you will more likely be able to hit multiple shards, meaning that you have to query all the data nodes for each query in order to find the documents that you're searching for. But in our solution, we don't have range-based queries, because if a user logs in, only the PDF messages are in MongoDB. So when a user wants to download a message, he can actually pinpoint that one specific message that he wants to download. So we're not doing any range-based queries. So, I mean, this was not really a problem for our specific solution. Now, if we go to the PSS architecture, that's how your normal 3-node replica set looks like. It's called PSS because that stands for primary, secondary, meaning all the data is stored on 3 nodes, which also means you need 3 times the amount of raw disk space. So in our case, storing 40 terabytes means having 120 terabytes of disk space. But remember when I said that storage is very expensive at this particular provider, so we had to bring down the costs. And we did this for switching from a PSS to a PSA architecture in MongoDB. This is also not really common to do. But how does PSA look like? Well, here you are. PSA is where you replace one secondary with an arbiter. So that's why PSA, primary, secondary, arbiter. And that arbiter is not a data node, but is only involved during elections. So when the primary fails, then the arbiter suggests that one only secondary will take it over. So now we only store data on 2 data nodes, and you only need 2 times the amount of raw disk space. So that really saves a lot of disk space. But this construction might seem handy in saving costs. It also contains drawbacks. So we had to go back to our client and get better requirements if the PSA is a viable solution for us. So during our client talks, they indicated that they prefer durability as most important requirement. Durability means that whenever a message is sent to a citizen, the data, so the real message, can never be lost. I mean, even if the system goes down or whatever, we should not lose any information. That's really, really important. But messages are delivered on a system-to-system interface, and these can be paused for a while without any big consequences. I mean, these messages are delivered to our system in batches, usually in the evening or in the middle of the night, and then we have a publish date, which is usually in the future, so we have some time for processing the message. But reading the message, that's a citizen which is logged into the portal to be able to read his message. Also, messages are never changed or never updated. I mean, the user can only read it or download it or delete it, but he can never change the message or update the message. So that's why we use write majority in our system, our PSA architecture, to make sure that whenever we write a message to the system, it'll at least hit both the data nodes before we do a commit. On a PSS architecture, so that's the primary, secondary, whenever one of the 3 data nodes fails, then one of the other one takes over, and if you're using write majority, you can still write to 2 of the 3 data nodes because at least 2 of them are active. So a failure in a PSS architecture has no consequences for the application whatsoever. But we decided on going to a PSA architecture with a primary, secondary, arbiter. This means that if you're using write majority, like what we are doing, that whenever there's a failure, the secondary will take over, but you will never get a write majority because there's only one data node to write to. So you will never get a majority. So this effectively means that our system becomes like read-only, as in you cannot write to it when it's in a failed state, but you can only read from it. So it is not ideal, but in our specific case, it's quite acceptable to our solution, and it saves about 33% of disk storage costs. So please keep in mind that if you make these kinds of decisions, that there are usually consequences, and the consequences have to be viable within your architecture, within your solution. So how does our production system cluster now really looks like? So I already told you some of the aspects earlier. We're using the PSA architecture, a primary, a secondary, and an arbiter. We only have 2 data centers, while you should effectively always be using 3 in these kinds of scenarios. And we have a sharded cluster of 10 shards distributed across 20 data nodes, so 10 primaries and 10 secondaries. So all the primary nodes are located in data center number 1, and all the secondary nodes are located in data center number 2, which is a relatively even spread. But then the arbiters, well, yeah, we decided to keep them on the primary node, but then off by 1. So arbiter for replica set 1 runs on the primary node of replica set number 2. And this is because if then one machine fails, for example, if a primary node fails, then the primary fails on, say, shard number 1, but then also the arbiter on that same machine also fails, but that's from another set. So we never have a complete failure of one replica set at one time. Anyway, the whole cluster is managed by a tool called Ops Manager, which is a tool from MongoDB. You can get that for free once you start paying the enterprise license, and that'll really save a lot of trouble in managing and looking at how your cluster performs. But then the backup, well, the backup is a real different story. So here we go. Normally, when you have a backup solution, you might tend to have some strategy like, I don't know, doing a full backup once a week and then an incremental one daily. But the incredible volume of the tens to hundreds of terabytes that we are starting with and eventually growing towards, yeah, regular backup is not really an option. I mean, doing a full weekly, like a weekly full backup, or even a daily incremental simply takes too much time. So how about our requirements regarding backup? Well, we have an RPO of 0, that's the recovery point objective, meaning that the backup has always be up to date. We can never lose anything. And the RTO, so the recovery time objective, is 4 hours, meaning that whenever the system fails and we need to restore, the restore has to be finished in 4 hours. But we are using a solution with unlimited lifetime of messages, and there are no deletes. I mean, the cluster behaves like a very big write once, read many times kind of approach. So our MongoDB experts suggested in using a custom streaming backup solution, which uses the predecessor of the change stream, which was introduced in Mongo 3.6, and that's called the oplog listener. And maybe you've heard me saying that before. Oplog is an internal mechanism. It's short for operational log, so it's actually just a log file, a append log file which writes all the changes, so the operations which have been performed, to a single log. And this oplog is an internal mechanism of Mongo to synchronize the primary with the secondaries. So whenever a new document is saved to the primary, this will be placed on the oplog, and the secondary will read this oplog and will then also save this document to his data store. Well, our custom backup solution uses this hook to directly make a backup and save this document as well as a file on disk. And then the solution becomes a continuous backup solution, which will simply follow the primary almost instantly. And also, the backup does not have to be a single process. I mean, please remember that our MongoDB cluster is running on like 10 primary machines, meaning we can have 10 backup processes at least, which are all running on their own primary and are only listening to changes for that very specific shard that the primary is working on. So in production, we have multiple backup processes running on multiple machines, and they are only listening to their specific subset of the data to backup. So, but then how do we do a RPO and an RTO? Well, since we're doing the continuous backup, we actually already have an RPO of 0, because whenever a document is saved, it is also picked up by the backup solution and is actually backed up as well. So this means that whenever a new document is saved, it'll be backed up within, well, usually somewhere between milliseconds and seconds. But then how about the RTO? So if the system goes down and we need to restore, how can we restore like tens of terabytes within 4 hours? Well, yeah, that's well, it's impossible. It's unworkable. Mainly also because of the very low IOPS. We are simply unable to restore that amount of data with that low amount of IOPS. So we suggested a compromise to our client, and the compromise is that whenever we do a backup from the old documents first and then going to the newest one. So they're in time sequence from old to new. So whenever we do a restore, we do a restore in reverse order. So that means we start restoring with the newest documents which has been added at the very latest point in time, and then slowly go back in time. This still means that we need way more than 4 hours to restore a shard, but we can make sure that we restore the newest documents within the first 4 hours, meaning that most of the users will actually only see the already restored documents. Because please keep in mind that the usage pattern for our system is that the users tend to view the most recent documents mostly, and if those documents become older and older, then the frequency on which they access these documents become way lower. So that means our client was accepting our proposal on doing a reverse restore in time, but then ensuring that most of the documents, at least the recent documents, were restored in 4 hours. And then because MongoDB can simply restore while running, I mean, the system can simply be switched on and be used by clients while the restore is still running in the background with only some degraded performance. So now let's go back to the upgrade. Let's go back to that point in the middle of the night where they were at the point of upgrading the MongoDB cluster. Well, it's very disappointing because they hit the upgrade button on the Ops Manager and, well, it worked. I mean, it upgraded each and every node one by one, disconnecting it from the cluster, upgrading the software, reconnecting, and then synchronizing. And that simply worked and completed within minutes with no issues whatsoever. So, yeah, that was pretty, yeah. So, anyway, maybe let's go back to the current size of the cluster. I mean, you might be wondering, with that expected growth rate, how big is your system now? Are you now the biggest system in the world? And that's also a bit, yeah, it didn't grow as fast as the client would suggest it, and it didn't grow as hard as we hoped it would be. But still, we are currently at about 40 terabytes, and we are almost too small now, so we have to start expanding our cluster to be more than the initial set of the 10 shards. But we are already live with the system for about 3 years, and we are processing about 90 million messages per day. So the growth rate is really a lot slower than the original expectation from our clients. So maybe 40 terabytes is not as humongous as I hoped it to be. I mean, it's still a very decent size, and it's still a lot bigger than most of the other systems that I've worked on in the past. And also, if you go to a big Mongo event and you expect a lot of customers to have very big systems, most of them only have relatively small systems, as in tens or hundreds of gigabytes, but we are doing tens of terabytes, so that's really 1,000 times smaller. So how are our expectations from the MongoDB? Because MongoDB is a new product, I mean, it's distributed, it's NoSQL, a lot of new concept, a new way of working, but our experiences have been good to very good. I mean, we have been working with lots of products from lots of different companies, companies with big names or fancy logos or blue logos, and a lot of those problems, a lot of those products have some really weird issues or need some serious workaround or other stuff like that. But for MongoDB, this is actually not the case. I mean, we haven't had any big problems with MongoDB except for some issues which were mistakes made by our people because, you know, we're new to the product. Also, we have got a lot of support from MongoDB on this project and they were always very fast and professional. Also, I earlier told you about how easy MongoDB is to use as a developer. For example, if we write a system and we're using a SQL database like a IBM database, then nobody has an IBM database locally on his developer machine. So if you really want to test some database specific stuff, you're actually hopelessly stuck. You need to deploy it to an environment where the database is installed and configured properly. But for MongoDB, this is not really necessary. I mean, you can simply spin up a MongoDB as a Docker container, for example, or I wrote a integration test to test the backup solution that we have, and it'll spin up a small sharded cluster even, and we're talking about only a small cluster, so 4 shards with 3 data nodes per shard, so that's like 12 Docker instances, and you also of course need some routers and config servers, so you're talking about 17, 18 Docker instances. But the whole cluster is up and running, including switching off the balancer and configuring the sharding as we do in our production environment. And it all happens within like a minute or so. And yeah, you can actually run then your backup scenarios and you do some testing and loading up your test data and performing your tests. And that can all be done on your local developer machine or on your build server or on your Jenkins. So I really haven't seen anything like this at this point. So personally, I would really recommend using MongoDB as it is a very good product. I really, really like it. And I haven't seen a lot of other products which are so very flexible in using and so very easy to use. So that's our experiences on MongoDB. Well, then that's all, folks. So I want to thank you very much on visiting this presentation, and I hope you've learned something. And whenever you want to know anything about this, please let me know and we can always have some discussion later on. Okay, thank you very much. Bye bye.